All right, hello, welcome back. Let's look at what orthogonal means. Well, the definition of two vectors being orthogonal is just that their dot product is the number 0. And it turns out that means the same thing as the two vectors meeting at a right angle. This theorem proves it. We'll look at that in a minute. But first, let's just draw some vectors to see, are they geometrically perpendicular, looking at the picture, and are they orthogonal using the definition. So let's start with A here. So the vector u is on the x1, x2 plane, also known as the xy plane, and v is on the x3 axis, like so. And yeah, if one of these is on the x1, x2 plane, and one is on the x3 axis, then they have to be perpendicular to each other because the x3 axis is perpendicular to the x1 and x2 plane. Are they orthogonal? Well, if we do u dot v, that becomes 3 times 0 plus 2 times 0 plus 0 times 1, which is 0. So yes, they're orthogonal too. Okay, so you can see when you have vectors where all the non-zero things line up with zeros, then yeah, the dot product is definitely going to be 0, and it makes sense that they would be perpendicular as well. Let's look at B. So there's the vector x at 1, 0, and the vector y is going to be at 2, 1. And does this look like a 90-degree angle here? No, it does not. So they're not perpendicular. Are they orthogonal? Well, if we do their dot product, we get 1 times 2 plus 0 times 1, which comes out to be 2 and is not 0. So they are neither perpendicular nor orthogonal. Let's look at C. C is a little more interesting because neither of these are like on the x1 or x2 axes. These are both like diagonal vectors. So this is what these look like. And are they perpendicular? Yeah, it sure looks like it. I suppose you could say that the slopes of these two arrows are opposite reciprocals of each other is one way to see it. You could probably use some trigonometry to show that that's a 90-degree angle as well. And are they orthogonal? Well, if you do the dot product, what you get is 1 times negative 3 plus 3 times 1, and that gives you 3 minus 3, which is 0. So yes. So yeah, it looks like, with these examples at least, that the dot product being 0 is equivalent to the vectors being perpendicular. And maybe before example 4, we can talk about this theorem that basically says that the angle between the vectors is 90 degrees, meaning perpendicular, if and only if their dot product is 0. This is going to be a homework assignment for you to prove it, but we can just look at the gist of it here. The gist of it is to show that the length of these two vectors, which are like the diagonals of the parallelogram determined by u and v, the lengths of them are related to the dot product of u dot v using this formula here. And you can sort of see why, if those lengths are equal, the lengths of the diagonals are equal, then the parallelogram is really a rectangle, and it means that like alpha and beta are each 90-degree angles. And I'll leave the details of that up to you. Anyways, let's look at this next important example. This says, suppose that u and x are any vectors in RC. Let's show that u and this other vector, x minus this scalar multiple of u, are orthogonal. So it turns out this is going to be really important in the next couple sections. This gives you a way of taking any two vectors and getting a vector that is orthogonal to one of them. So to show that they're orthogonal, we need to show their dot product is 0. So our goal is to show that this dot product is 0, and if we can, that means these two vectors are orthogonal. So the first thing we can do is use a distributive rule that we have here. It was this one. Write this as u dot x minus u dot the scalar multiple of u. Oops, I wrote the 0 vector, but the dot product is just a number, so we want to get the 0 number from this. Okay, at this point, remember these dot products here are scalars, so we can just multiply u and take the scalar out of it, which was property number 2 here. So we can do that. And then we notice that u dot u is the scalar in the denominator multiplied by this other scalar u dot u that will cancel out just using regular fraction rules. And what you get is u dot x minus x dot u, and we know those are equal because of property number 1 here. So when you subtract them, you get 0. So yeah, that means they are orthogonal. All right. We also have theorem 5.4 is the Pythagorean theorem. Now, you might be saying, wait, the Pythagorean theorem, didn't we kind of just like assume the Pythagorean theorem was true when we defined length? And yeah, we kind of did. I mean, we defined length to be the square root of this thing, and knowing the Pythagorean theorem, we know that this agrees with the physical geometrical concept of length. But that was just our definition, and using that definition and also other things we've proved based on it, we can prove like the more general Pythagorean theorem here, that two vectors are orthogonal, meaning this is a right triangle if and only if the length of one side squared plus the length of the other leg squared is equal to the length of the hypotenuse squared. And the length of the hypotenuse we know is the length of u minus v, like we showed before. So we don't want to use the Pythagorean theorem to prove it that you learned years ago. We can just use the linear algebra definitions we have so far. And that is going to be a homework assignment for you. In the next video, we are going to go into stuff that is probably completely new to you, even if you've done orthogonality and dot products in physics and calculus before, which is orthogonal complements. So we will look at that in the next video. See you then.